Okay, going over digital logic basics, and I'm going to do this by showing you how to take W equals, and you would read this A and B or C, because remember, multiply means an AND gate, and the addition symbol means an OR gate. That sort of comes from Boolean algebra, the work of Claude Elliott Shannon, who showed a correspondence between digital logic and Boolean algebra. So all you need for now with that is wherever you see what would be multiplication, think and wherever you see addition, think or. So this means A and B or C. So we're going to look at this circuit 4 different ways. We're going to look at a digital logic diagram. We'll build it on a digital logic simulator. We'll do a wiring diagram. And then normally, if it wasn't shut down in class, you'd actually get to build it. So we're going to have to build it on a component simulator. Okay, so let's get started. Our digital logic simulator. So that's the first thing we're going to do here. Sorry, digital logic diagram. So our output is W. So I'm going to put the W over here, put my outputs on the right. And your inputs are A, B, and C. So I've got an input A, B, and C. Now, we're not going to do the addition, which is the OR gate first. We're going to do the multiplication first. This follows the same order of operations as BEDMAS. If you wanted the OR functionality to happen first, you'd have to put that in brackets. You would have to have a bracket here and here to indicate that it was B or C, then ANDed with A. So following BEDMAS, we do multiplication before addition. So we do our ANDing before our ORing. We're going to have A and B. So I'm just going to draw an AND gate that connects A and B. So that makes the result on this wire here A and B. Now you don't have to write those in, but when you start, you probably should just to learn what it is you have. I now want A and B or C. So this is my line C. So right here I've got C. Here I've got A and B, and I want them connected with an OR gate. So I'm going to put an OR gate here. So an OR gate looks kind of like an AND gate, except it's pointier here and it's curved here. So now I have A and B or C as required. So I'm all done. That is my digital logic diagram, and it indicates to me that W is equal to A and B or C. Now I'm going to build this on a digital logic simulator. And in the work I assigned you, I put a link to a useful one here. Okay, so this is Circuitverse, and I want a digital logic simulator of A and B or C. Okay, so I need 3 inputs. They're going to be A, B, and also C. And I need 1 output. That's my W. Okay, so this is A, B, C, and that's W. Now, these should be labeled. There's a text box. Okay, bear with me. I'm a little old and kind of slow on the computer here. That's B. And over here we've got C. Okay. And our output, we're calling our output W. Now, because the circuit is so small here, labeling things doesn't seem all that important, but As your skills develop, so does the complexity of what you're able to build, so it is important you get things labeled. Okay, now in between those, so just following my logic diagram, I want an AND gate, and I want the inputs to have A and B on them. So I'm going to go over to gates, choose an AND gate, and then I'm just left clicking to get that wire. I'm going to connect A and B. So I want A and B going into an OR gate, and I want C going into that same OR gate. So I've got my OR gate here. From what I recall, if you're in England watching this, you use different symbols. I think you just use a rectangle and you write the name of the gate in there. These are the American symbols. Although with everything on the internet these days, I'm sure the symbols are more unified. Okay, so here I've got A and B. Here I've got OR C. And if I just change those, you can see how that wire here is bright green when it's on and dark green when it's off? See how with this being off, that is off. And here's my output. Okay, now let's verify it. If all of them are off, so our truth table with A, B, C all being off, W is off. Just A on, it's still off. If I have A and B, it comes on. So remember, 1 is on, 0 is off. If I have C alone, it comes on. So the functionality of this is A and B or C. So you need both A and B for W to come on, or you need C for W to come on. Now, an interesting thing looking ahead, what if you have both A and B and C? Well, it still comes on. There may be times where you exclusively want A and B to turn it on, or C, but not both. This could perhaps be two different things making a request, and the request can only be served by one or the other at a time. And in such a case, you would use this. This is similar to an OR gate, except this exclusive OR gate will not come on if they're both on, but you'll learn about those later. All right, so this is the simulator, and what I want you to do is hand this in as an image. So go to click on download as an image, put that into the OneNote so that I can see that you've done this. And that is your logic simulator. So our digital logic simulator is now complete. Okay, next thing I want is a wiring diagram. Now, a wiring diagram is going to show somebody else how to build this circuit using components. They might not necessarily even have to understand what it's doing, but they certainly have to be able to put it together and make it work. So think yourself as giving instructions to somebody who's going to build this for you. So everything has to be dead clear. So on the wiring diagram, we need an AND and an OR gate. And we're going to assume that we're getting them on two different integrated circuit chips. And to start out, we're using 7400 series ICs. So just notice I've got 14 pins on each of these. And the way these work, 7408 is a data sheet for an AND gate. VCC means the common collector voltage, and GND stands for ground. This is going to be connected to 5 volts, and this is going to be connected to 0 volts. So let's keep things labeled. This is our 7408, I believe. Yep. So that's our AND gate. And we've got 5 volts at the top. We'll put 0 volts at the bottom. And we're going to connect pin 14 to 5 volts. So I'm going to show that pin 14 is connected up to 5 volts. And over here, pin 7 is connected to 0 volts. I'm going to do the same thing with our OR gate, which is, I believe, 7404, but just let me quickly double check. No, that's not an OR gate, that's our NOT gate. 7400 is NAND. Okay, my apologies here. 74 series. All right, and then let's quickly find a list and okay, it's 7432. All right, so this is going to be a 7432. That is our OR gate. Okay, so this is powered up. And so let's get a 7432 data sheet. And you can see, so there's our OR gates, and we get 4 of them on here. And pin 14 is VCC, pin 7 is ground, and this goes input, input, output. So that means we have inputs here, and an output here. And same thing with the AND gate. Have a look at this data sheet for our AND gate. We've got, as we look at the bottom and go left to right, we've got 2 inputs followed by an output, 2 more inputs followed by an output. Now, when you actually have this chip in your hands and you're putting it into a board, you wouldn't be able to tell which pin is which. There are not numbers on them. However, there's a notch here. So from that notch, you go counterclockwise and then count up 1, 2, 3, 4, 5, 6, 7, and then they keep going counterclockwise. So opposite of a clock, starting at the notch. Okay. So now we've got to make these connections based on our digital logic diagram or our digital logic simulator. So A and B go into an AND gate. This is our AND gate, and these are the inputs as per our data sheet here. If I can copy that here. Not showing up. All right. So we have our inputs are A, B, and C. And I want to show that A is one input here, and B is the other input here. So A and B are each, erase that to make that clear. A and B are each inputs into our AND gate. C is the input to our OR gate. So you can see here, C is the input to our OR gate. And our OR gate has inputs here and here, and then an output there. So I'm going to show that C is an input to our OR gate. Now back to your logic diagram. The output of the AND gate is the input to the OR gate. So the output of the AND gate is the input to the OR gate. And then finally, the output of the OR gate is our output W. Over here I've got inputs, and over here I've got an output. And I've got 5-volt power supply, and 5-volt is connected to pin 14 of each of these chips. That's not something to memorize, it's something to look up. So depending on what chip you're working with, you want to look up where the power supply is. Notice in these 7400 series that you've looked at so far, your power supply goes in pin 14 and pin 7, but that's not always the case. There are several op-amp chips where you're going to power them in the middle. So case by case, you want to look at the data sheet each time. Okay, so that's your wiring diagram, and somebody with that diagram would be able to put this together, and we're about to do that. Now, we're at home working on our computers, so we're not putting these together, but we will simulate putting them together in Tinkercad. Now, when you click on Tinkercad, you are going to have to log in. And in order to do so, you'll go to, I'll send everybody the class code, and then you're going to have a nickname, and that's how you're going to get in. And then once you are in Tinkercad, make sure you click on circuit. So we're not doing 3D designs, we're not doing code blocks, we're doing circuits. Okay, so click on create a new circuit, and you have these components here. And what I'm going to ask you to get is a breadboard. So this is a plastic board that has metal connectors underneath. And the way this works, everything in this row is connected. And see how it highlights that? See what all shows up in green when I go on here? Everything at the top and the very bottom horizontally is connected. In the middle, everything vertically is connected except not across that gap. So that's a breadboard. Now we're going to get some digital logic gates. So if we go to all components, and over here we've got integrated circuits. So I'm going to look for let's do a search for it. So my 74HC08, that's my AND gate. It says quad because there are 4 of them on there. And I'm going to drop that into the breadboard right here. And I want my OR gate. We'll just do a search for it here. It'll probably give us a 7432. Oh, it looks like I'm finding the word OR anywhere in there. All right, so let's go with 74HC32. See if that's, there we go. So that's our OR gate. Okay, now I'm doing this wrong on purpose. See how I connected it here? Problem with connecting it like this is it will connect this pin to this pin and that pin to that pin, because a breadboard connects everything vertically here. So you want your IC chip to go across the gap. Okay. So I've got these 2 gates as per, looks about the same as my wiring diagram. Oh, and the wiring diagram is done, so let's check that off. So our wiring diagram is now done, and we're now doing our component simulator. That's what we're working on. Okay, so I need 3 inputs here. And the way I'm going to make my inputs, now A digital logic input is not just a single switch. It actually has to be what we call a double throw switch. And the reason why is you want to either connect the pin to 0 volts or connect it to 5 volts. You don't want to choose between connecting it to 5 volts and having it completely disconnected. You need to set it to 0 volts. So the way I'm going to do that is by getting a slide switch. So I'll have one for A, one for B, and another one for C. Now see how it's overlapping with these chips here? I'm going to have to move them over. And I'm going to put that in the middle here. There we go. Okay. So these are going to be my inputs A, B, and C, and then I need an output, and I'll use an LED for my output. And we'll keep working left to right here for now. And no, I'm not going to switch that. Okay. Now, when you look at this LED, notice this is the anode and that's the cathode. Oh, it even labels it here. So the longer leg is the anode, meaning it has to be connected to the positive end of the power supply. Because an anode draws anions, and anions are negative ions. However, I digress. This is in chemistry. Okay. Now let's get our power supply attached. And should we use a Zener diode and make a proper 5-volt power supply? I'll show you that in another video. Let's just use this 3-volt because it's going to work just fine. We'll keep this a little simpler. Okay, I'm going to connect that rail to positive, and I'm going to connect my negative rail to negative. So this sets me up to build this wiring diagram here because I've got my 5 volts up here and I've got my 0 volts down here. Maybe towards the end of the video, I'll make a power supply to switch that to be a proper 5 volts. All right, now my inputs A, B, and C have to go A and B here, and C has to go there. Now watch very carefully how I do these inputs. I'm going to connect the middle. The middle of that switch is the input. That's going to go here to this pin. So I am making this connection here. A goes to this pin. The middle of B, it's got to be the middle, is going to go to that pin. And the middle of C, I'm going to put over here because notice when you look at our wiring diagram, C is connected to the input of our OR gate. So remember our OR gate, if you look at a map of that chip, you've got 2 pins going into an OR gate, and then there's an output. And then you've got 2 more pins going in as the input, and then yet another output. And then this is GND, which stands for 0 volts. Up here is VCC, which stands for the voltage of common collectors, and that is your 5 volts. Okay, so this wire here is input C is the input of our OR gate, and I've done that here. I ran this wire across here. Now the output of our AND gate is the other input of the OR gate. And see how it doesn't matter? I don't have to put it right up there. I can put it anywhere in this column because on these breadboards, everything in a column is connected. Finally, the output of my OR gate is the output. So I'm going to make that the anode of the LED. And then I just need to connect my LED to 0 volts. And I'm going to do so through a resistor because otherwise that LED might burn. So I'm going to grab a resistor and I'll run it up here. So see how that resistor now connects the negative terminal, which will be 0 volts, to the cathode of my LED. Because I'm going to run a wire there. Okay, so in practice, all of these green lines would be wires that you would be running across your breadboard. And remember, on your breadboard, it makes vertical connections here, horizontal connections there, and then there's no connection across the gap. So the components I'm putting together here match this wiring diagram, and again, this wiring diagram matches this digital logic diagram, which in turn matches this Boolean algebraic expression. Okay, let's keep going. To get these these inputs to work, we want these switches, when a switch is thrown, to go from connecting this to 5 volts or to 0 volts. So I'm going to connect the left up here to 5 volts. And I'm going to connect the right to 0 volts. Now, that's not going to be 0 volts unless I connect it to 0 volts, which I will do here. I wonder if I can run that out just so it's not in the way. All right, so both of these black lines are 0 volts, and that red line there is 5 volts. Okay, do I have everything connected? So my inputs here, the way the switch works, when the switch is on the left, it's going to connect this pin to this pin, and when the switch goes to the right, it's going to connect the middle pin to that pin. So they're called terminal 1, common, and terminal 2. So with the switch on the left, it is connecting the positive end of the battery as the input to my logic gate. Now, I think I forgot, yeah, I did not power these gates yet. So to power them, see that's power and that's ground. So this is the power line here. I'm going to connect VCC of each of those two gates up here to 5 volts. And then this is ground down here. I'm going to connect ground to 0 volts. So I've got it here and here. Okay, I believe that's everything. So let's start the simulator. Now the light's coming on. Remember, this is A, B, C. So let's turn them all off. And see how the LED is off. Now if A is on and B is off, it's still off. If A and B are both on, it comes on. Or if C is on, it comes on. So I've got A and B or C. Now, it automatically gives you names here. So this is going to be, I'll label that A and B. I don't know if it'll let me put in a plus sign or not. There we go, yeah. So I'm going to label the file A and B or C. And I'm going to ask you to share that with me, or you could screenshot it to verify that you've actually done this. So on Tinkercad, what I've done here is I've done my component simulator, which is the next best thing to building this. It would be better if you'd actually build it, because you're going to find in practice there are always practical matters and hands-on skills that are better for you to acquire. Okay, so let me recap. We started out with a Boolean algebra expression. W equals A and B or C. Remember, multiply means and plus means or. And you've been assigned to do a logic diagram, logic simulator, wiring diagram, and component simulator. On the logic diagram, we put our inputs on the left, our output on the right, and we make the appropriate connections as outlined here. We're following the order of operations. In math, that would be multiplication before addition. So in this, it'll be anding before oring, unless there are brackets to indicate otherwise. So I've got A and B, or C. And by going left to right and labeling the wires with the expression, that makes it easier for you to follow as you get started. Okay, the next thing is the digital logic simulator. So the digital logic simulator, I have a link to, or if you're not in my class but you're just watching this to learn, I'm using circuitverse.org. And this is going to match that digital logic diagram that was done. And when you click on these, you should see that it it works. If A and B are both on, that should be on, and 1 indicates on in the digital logic simulator. And if just C is on, it'll be on. But if C is off and we don't have both A and B, it's going to be off. For our wiring diagram, it won't really make a lot of sense to you what you're doing until you've built a few simulators, and then you realize, oh, okay, what I'm doing is making a map as to how you'd build this on a simulator. For your wiring diagram, you want to find the integrated circuit chips, pin out maps that match the functionality that you're building. And then you want to very clearly show where the power supply is connected, where the inputs are connected, and where the outputs are connected. The wiring diagram should tell the exact same story as your digital logic diagram, except it is more instructional in how to build it. However, it's less obvious as to what it is it's doing. That's why we work with both. And then finally, following your wiring diagram, I want you to build this on a component simulator. Now, to be realistic, you're probably going to build it on the component simulator and then retroactively make the wiring diagram, and that's fine. You're going to do that for the first few, because at a smaller scale it's easier, and then once you have some familiarity with it, it's actually going to be easier to plan it out before you build it. And class, you're going to hand in all 4 of these. So to hand this in, you're going to either share it with me or do a screen grab so I can see just the image here. Same thing for this. Well, if you click on here, it'll let you download the image, and then you can put that into your OneNote. And you're going to also give me both of these drawings. You can draw them directly into a OneNote or on Paint or whatever it is. But really, you should freehand draw it, because that in itself is a skill as well.